Hello children, welcome to channel Sube. Children, today I am going to discuss question number 34 from the MCQ part of 2021 Physics New Syllabus paper. A uniform magnetic field of flux density capital B equals 1 Tesla and a uniform electric field of field intensity capital E equals 300 volt per meter are parallel to each other in a region as shown in the figure. So these are electric fields shown in dashed lines. These are magnetic fields shown in thick lines. A particle of charge plus q enters at a velocity v. So this one, velocity equals 400 meter per second, perpendicular to the fields and directed into the plane of the paper. They have drawn a cross here, that means the particle enters directed into the plane of the paper. The magnitude of the resultant force acting on the particle is 0, 100 q, 300 q, 500 q, 700 q. So children, let us try to solve this problem. Let us mark this magnetic field using red color, because I am doing that so that you can understand easily. In the real time examinations you don't have to do these things. So the magnetic field strength capital B is given as 1 Tesla. 1 Tesla. So let us first of all consider this magnetic field. Let us forget for a moment this electric field. So you know children, when there is a conducting wire and there is a current, say I, into the paper across here like this. So current means positive ions. So when there is a current into the paper and there is a magnetic field like this, B, perpendicular to the current like this, so there is a force. There is a force. That force is called the magnetic force. Magnetic force. If this one is a wire, conducting current, if the length of this wire is L, you know the force acting this way or whatever the direction, still we don't know, but the magnitude of the force is equal to B L BIL. This formula, this equation you know, BIL. The force is given magnetic force. This one is magnetic force. Magnetic force is given by B times I times L. So the length is L. But here there is no such conductor. Only the particle. Only the particle is moving towards the paper. So only there is a velocity. So we can mark all these things. So there is there isn't a wire, only a particle is like this. There is a particle like this, whose charge is simple q. So then that also experiences a force when there is a magnetic field capital B. So what is the equation for that force? Magnetic force. So there is an equation B Q V. V is the velocity. So you must remember this equation, otherwise you can't solve this problem. B Q V. So this is the equation now we are going to use. So to find out the direction, because they are asking the magnitude of the resultant force acting a force, so we have to find out the direction definitely, because to find out the resultant there must be actually two forces, so we have to find out the resultants like this. So direction of this force, magnetic force, you must know first of all. So to do that, to find out that direction of the magnetic force, what we use, what is the rule? What is the rule we use? That is called Fleming's left hand rule. So I am going to remind you what is Fleming's left hand rule is. If we arrange our thumb, forefinger and middle finger of the left hand perpendicular to each other, so there is a figure like this, thumb, then forefinger and middle finger perpendicular to each other like this, so perpendicular to each other, left hand, then the thumb points towards the direction of the force. First of all we have to say, before talking about thumb, you have to first, because what we know is normally this field intensity, the flux density is given. So first of all you have to direct your forefinger to the forefinger points towards the direction of the magnetic field. So this one should come first. The forefinger points towards the direction of the magnetic field like this, and then you have to rotate your palm so that this middle finger is directed towards the direction of the current. Then from this thumb you can find out the force acting on a conductor. If it is a conductor, you can find out the force, the direction of the force acting on the conductor. If it is a particle, that way also you can find out the force on the acting on the particle. So this is the Fleming's left hand rule. So now we are going to use it to find out the direction of the force acting on this particle. So let us take, instead of the particle, the current, the direction of the current is to this way. Direction of the current is to this way. So let us use some other color, purple color. This one is the current. Current. So B we know already. So we have to find out the force, direction of the force. But here you had used this diagram, not this one. I drew this so that you can get help from it to understand. So let us use our hand, not this one. I have arranged a hand which is suitable for our diagram. So let us use this, because I can't rotate this picture, this figure, I can't rotate this, therefore I have a hand like this. So they say the positive particle, the positively charged particle, this one is moving into the paper, so the current is to that way. So therefore the current is indicated by the middle finger. So this one, middle finger. So we have to place the middle finger like this, so that it is directed into the paper. So then at the same time you have to turn your forefinger towards the direction of B. So B is given, so the arrow is here, you can see. So to that way you have to turn your hand, but not changing the first one. That means the middle finger you have to keep constant without letting it change. Then you can rotate your hand like that. Then there is a direction to which the thumb is directed. So this one. So that is the direction of the force acting on that current. Current means the charge, because the charge is a positive one. So we know current is a flow of positive charges. So therefore you can use the word current instead of this positive charge. Therefore now we see the force is downwards. Force is downwards like this. What force is this? This is called the magnetic force. Magnetic force. This one. This one is magnetic force. So now we need the magnitude of that. Magnitude of this magnetic force. So using this equation we can substitute F equals, B is given 1 Tesla. Here you see 1 Tesla flux density, that is flux density. The charge is not given, that is we have to take as Q itself. So velocity they have given. What is the velocity of the charge? 400 meter per second. So that we have to substitute here. Then we get the force equals to 400 Q. 400 times Q, that is the force. So we can write it here 400. Let us take a little bit right, like this. This force is equal to 400 Q. Force is equal to 400 Q, that is the magnetic force. So let us now consider the electric force. So they have given the direction of this electric field. So this line is called lines of fields, or just we can say field lines, lines of field, or force lines, we can say lines of force. So this force line is directed to this way, to the right, from left to right. So what is the definition of that? The force line, the line of field, is the path of a positive charge. That means if the direction of the electric field is to this way, and if we released a positive charge, if we released a positive charge like this from this place, so what happens? This positive charge automatically moves along this path. On this path, that means it moves on this path, means to this direction. So that is what these lines of fields mean. So they have given that. They have given that. So we don't have to find, we don't have to worry about the direction of the force, because this is the force acting on this charge. So they have given it. So unlike we were trying to find out the direction of the force using this in this magnetic field, so it was difficult. Using left hand, we had to use left hand to find out the direction of the force. But here it is very easy, because they have given the direction of force lines, electric force lines, and here arrows are there. Direction is given. So then that means this particle is moving that way, or there is a force to that way. So therefore now we know the direction of electric force. Electric force is to this way. So it is easy. So what is this? Electric force. So now we know the direction of electric force. So to understand easily, I color this line, the electric line, using the same color, blue color. So this one is the electric field, capital D. So how to find out the force, the magnitude of this force? There is an equation, F equals this one, F equals EQ. E is the field intensity or flux density. So they have said field intensity, both words are used. You can say either flux density or field intensity, capital D. It is given 300 volt per meter. So let us substitute it. 300 times, Q is not given, so we have to use that symbol instead of the value. So F is that one. So we can write it here now. So electric force is equal to 300 Q. So what they want us to find out is the resultant force. So let us use the vector diagram to find out the resultant. So you know this one is the resultant. So how to find out this? You can use Pythagoras theorem. So the value of final f is given by root 300 q square plus 400 q square. So you don't have to calculate this actually. If you know 3 and 4, then you get 5. So 500 q is the answer. You don't have to calculate, 3 to 4 to 5, then 6 to 8 to 10, like that. The relationship coming from the Pythagoras theorem is like that. So you remember this one. When there is a 3, when there is a 4, surely, definitely the value is 5. So therefore the resultant is 500 q. So the answer is this one, 500 q, the fourth one. So let's check the answer. 34, the answer is fourth one. So correct, answer is correct. The answer is the fourth one, 500 q. So I think you can understand this is not a big issue. So I explained how the magnetic force is calculated and also the direction using Fleming's left hand rule, and also I explained how to get the electric value of the electric force and also the direction. So the direction is exactly to the field intensity, to the direction of field intensity. So the force and field intensity are same in direction. So they have given this direction, so the force also to that way. So therefore it is not difficult. It is not perpendicular, something like that, as in these magnetic fields. Magnetic fields always perpendicular. The force is perpendicular to the flux density, but here the force is parallel to the flux density or the field intensity when we use electric fields. So that is the summary. So let us wind up this problem. We have successfully solved it. So now children, how do they give these magnetic fields and electric fields like this? That is the physics. So we just using a diagram like this solve these types of problems, but that is not real physics. Physics is how we make these magnetic fields and electric fields. So that is the main thing. So let us discuss that. I will show you how to do it. So to create a magnetic field and electric field, let us first discuss how to create the electric field. So to do that, you need two iron plates like this. Two iron plates like this. You place it at the beginning, at one end of this field where you are going to create this field, and the other plate you have to keep like this. Place it like this at the end of the area where you are going to make this electric field. So I can fill this using this blue color because I am going to create this electric field. So you have to use now batteries. So DC power supply, whatever it is, DC power supply or batteries, positive side to this way. We need a little bit higher voltage for that, at least 60 volt we need. So now you connect this plate using a red wire, because this side is the positive, this side is a positive. Then using a blue wire or black wire, you have to connect it to this other plate like this. So this side is the negative. So from positive to negative there will be a electric field like this, electric field like this. So that is how we create that electric field. So here, if you know the how do you know this value? They have given this as 300 volt per meter, the strength, intensity, the field intensity. How do you give that 300 volt per meter? That is strength, field strength. How do you give it? You have to adjust it. You have to adjust this voltage and this distance until you receive this value. So it is done like this. So this distance you have to measure. First of all, this distance you have to measure using a meter rule. So if it is D, suppose it is D, then this voltage, if it is V, you know there is an equation, E field intensity equals minus dV by dx. So you can forget this D and also negative sign, just V divided by D. X is D here. So field intensity is that value. So suppose this D is 20 centimeter. 20 centimeter. Suppose this voltage of the battery is 60 volt. Then let us calculate what is the field intensity, E. So substitute those values, 60 volt divided by 0.2 meter centimeter, 20 centimeter is 0.2 meter. So 600 divided by 2, 300. The value they have given in the question, volt per meter. So this is how we fulfill that condition practically. Practically this is how we do it. So you better know these things, because in structured paper they might give these things, and also in essay paper they can give these things. So now let us discuss how to create that magnetic field. The easiest way is to place a magnet, permanent magnet like this. A big magnet, if you have a big magnet, you can place it here like this. A U-shaped magnet is the most powerful one. So you can use such a magnet like this, permanent magnet like this. Sometimes we call this horseshoe magnet, sometimes we call U magnet. So the S pole to this say, S pole you have to place this say at this side, and N pole you have to place at this way. So N to S, the force lines are flowing N to S. So north side this way, south side this way. So N to S, the magnetic flux is directed like this. So you can receive this field like this if you arrange like this, a magnet. So otherwise you can do, but the problem is you can't find out the value of B, 1 Tesla. So that they said it is, the strength is 1 Tesla. So now let us discuss another way you can make a magnetic field here instead of this permanent magnets, because if we used permanent magnets we can't find out the strength, flux density, field intensity. We can't find out that they have given this as 1 Tesla, but we can't find out whether it is 1 Tesla or something else, because using permanent magnets, that problem we have. So therefore we can use electric current instead of these permanent magnets like this. So you need 2 big coils. Sometimes you can find out that from an old grinder that are used in kitchen. You know, there are blenders and devices like that having motors inside. So some old one, broken one, you can use. You can get the coil out of that, and you can try it. So this one, say this one is the coil. You have to place that coil like this. A big coil is there. So the coil has several turns like this. I draw a few. So there are lot of turns, about 100, 200, so something like that. But I draw a few. So then the other coil also you have to place somewhere here, like this. The 2 coils. The coil is like this. You have placed. So then you supply DC current to these coils, connecting them series like this, and take this wire, and you have to supply DC current like this. Then there will be a magnetic field between these 2 coils like this. So you can make like this the required magnetic field. So that is easier, and also you can calculate the field intensity using the equation. You know the equation, I am not going to write it, that is homework for you. So if you know the radius, if you know the number of turns, and then you can find out the flux density of these 2 coils, and in between these coils at this place. So you can find out the magnetic field intensity. So that way you can give a magnetic field. So that is how these things are done in practical in laboratories. So children, I think you understood it. These types of things they give in structured paper and also in essay paper. So you should be aware of these things. That is why I am discussing these things, so that it will help your essay paper and structured paper. And even this thing what I discussed about this electric field. So I can make you a small target question like this. So this is our target question. So they alter this problem like this, place into plates like this, as I explained you, and they connect it to this battery using wires. So they don't give the direction even of the electric field, because looking at the battery's polarities, you should be able to decide the direction of the electric field. So therefore I delete this, that is the magnetic field, these arrows. So these arrows are not given. The direction you don't know, but if you know what I explained, then you can find the direction. So let us delete like this the arrows. you don't need arrows. So now the field intensity is marked here like this. This one is the E. So B is also marked here. Everything is there. So they give this battery voltage, say 60 volt, as I said, 60 volt. Then this distance 20 centimeter, like this they show it, the distance, and they mark these are what? Iron plates, iron no copper. So like this, copper plates, and they change the question like this. So children, this is my target question. So I finished the diagram. So like this, copper plates are there at both ends, and battery is connected, voltage is given, the distance also is given. They have not given the direction of the electric field, just they have said this is E, capital E is there, capital B also is there, and Q charge is there as previously. So the question is a uniform magnetic field of flux density capital B 1 Tesla and a uniform electric field of field intensity capital E are parallel to each other in a region as shown in the figure, but they have not given the value. Previously they gave that 300, but I deleted it because you can calculate it from this given data. A particle of charge positive Q enters at a velocity of 400. Other all things are same as previously. So this one new. The distance between copper plates is 20 centimeter and the voltage of the battery used is 60 volt. The magnitude of the resultant force acting on the particle is same answers. So now I think you can do this. This is a new question. So they might just alter little bit of the past paper question and give it as new questions. Next time when you are sitting to the exam, you might get something like this if you are lucky. The same thing you have to do. Additionally, you have to find out the electric field intensity. How to find out? I showed you. So you do it now as an exercise. So these types of little change they do and give the same questions again and again. So if you refer to the past papers, that is something we can notice. So very little is changed. So additionally what you have to do is they have not given this field intensity of the electric field, so you have to find out it. That is all. That is the only thing you have to additionally do. So I think you can do this as an exercise, so do it. So children, I think you are happy. I did lot of things, basically I explained how to solve this MCQ problem, and after that I recalled, I reminded you what is Fleming rule and how to arrange your fingers so that you can solve that problem, and also I gave these equations and I explained what is this force lines are, what are these force lines are, and also how to solve this problem and get the answer using the Pythagoras theorem. And also I explained how to do this in practically how to do this, and also I gave you a target question also like this. So I think you are happy. So if you are happy, please make me happy also by subscribing my channel, but don't do it twice. If you have already subscribed, you don't have to do it. See you tomorrow. Goodbye.